Hello, everyone, and a very warm welcome to this webinar today, where we're talking about immersive audio and quality development in digital meetings. My name is Jeppe Lindegaard. I am the event and project manager here at Danish Sound Cluster. And Danish Sound Cluster, for those of you who don't know us, we are a member organization in the sound industry, and we are facilitating the sharing of knowledge, technology, and research to stimulate collaboration in the sound community and spread sound awareness in society. So if you want to, you can follow us on YouTube and LinkedIn. And today we have two very, very bright and experienced engineers. We have Markus Multrus from Fraunhofer and Stefan Bruhn from Stolpe Laboratories. And I will give you a short introduction to both of them. Markus Multrus is an accomplished figure in audio signal processing with a diploma degree in electrical engineering from Friedrich Alexander University in Nuremberg. Since he has been pivotal in audio codec development at Fraunhofer, focusing on waveform and parametric speech coding and bandwidth extension. His publications cover topics such as background noise, compression efficiency, and computational complexity, showcasing his expertise and experience in coding. Markus's proficiency in psychoacoustics and speech technologies underscores his status as the leading expert in the field. Thank you very much for joining us today. Markus, maybe just do a quick wave. Stefan is a distinguished figure in the realm of speech coding, boasting a PhD in electrical engineering from the Technical University of Berlin. Since he has been a cornerstone in Ericsson's endeavors, contributing to the development of various 3GPP speech and audio codecs. With decades of experience at Ericsson, Stefan has amassed a wealth of knowledge and expertise in speech coding technologies. His contributions have not only shaped the evolution of speech codecs, but have also impacted the telecommunications industry's standards. Stefan's portfolio goes beyond his professional achievements, with more than 10 patents to his name, attesting to his invaluable contributions to the field of speech coding. So thank you very much, Stefan, for joining us, and a warm welcome to you as well. Now, before I will leave the floor to both of you, I'd just like to ask a couple of questions, because I'm very curious, obviously, about all your technical expertise. But Markus, maybe you want to start here, since you've worked very closely together with Stefan. What do you like the best about about Stefan as a collaborator?
So, so I've worked together with Stefan already for quite some time. I think we first met in approximately 2010, I think, when we did the development of the EVS coding standard together. Back then, Stefan was still at Ericsson. So what I really like about Stefan is really his not only his technical expertise, but also his expertise in standardization. So he's really the right man to drive standardization efforts in a good manner and to make that really a success.
Okay, and Stefan, I would like to ask you the same. What can you?
Yes, yeah. So of course, I like Markus. Of course, very much as a very good colleague. So essentially, well, of course, with all his experience, technical background, expertise, it's very easy to make good developments and standards with Markus. So taking things together. I mean, sometimes our companies are competing, but still we usually find good ways forward in discussions, and maybe also sometimes in kind of argumentations to find the best way. And I think what I very much like with Markus is that that what we agree does work, and together we are very successful. So this is what I like very much.
Cool. Okay, thank you for sharing and give just a bit of insights inside your machine there. So for those of you who have just joined us, I'm sure that some of you came in here a bit late, which is just fine. But today we're talking about immersive audio and quality development in digital meetings with Markus from Fraunhofer and Stefan Bruhn from Dolby Laboratories. So now, without further ado, I will leave the floor to you two gentlemen. And Markus, please share your screen and take it from here.
Yes, and so I will be the one who will start presenting. So actually what Markus and I will be presenting is not work from just the two of us, but it's actually the work of many names here. You see here a list of 11 companies. So these 11 companies have together developed the new 3GPP codec for immersive voice and audio services. And well, what is important to know, of course, is 3GPP. 3GPP is the standardization umbrella organization for all mobile standards. It started with UMTS, and then it did LTE and now 5G standardization. So this is what 3GPP is. And here these the companies that are listed here, and the people listed there have all contributed to the codec. And these are actually the team leaders. So behind the work that we are presenting here are many more contributors. So actually, we can almost multiply the names that you see here by, I don't know, a factor of 5 or 10. Maybe 5 is more fair to get the real number of contributors. Most likely even more than 5. So what I'm presenting here is actually very fresh. We presented similar things at the IEEE ICAS conference 2 weeks ago in Seoul. And what we present you here is essentially an adapted version and shortened version here for this webinar. Please, Markus, next slide. So the outline of the talk is that I will start first talking a little bit of the background of the IVAS codec. We'll discuss a little bit of what we understand as IVAS-enabled services. Then I hand over to Markus, who will bring us closer really to the technology that is underlying the codec. So there is, of course, since it's a spatial codec, there is a lot of technology spanning essentially from a core coder to some kind of spatial coding principles that need to be done. There's something on rendering and capturing that are very important if we have to deal with immersive audio. Then Markus will bring us some overview of the IVAS codec characteristics. After that, I will take over again, give you just some kind of impression of what the 3GPP IVAS codec means in terms of its standard specifications. And well, in the end, there will also be some kind of intro to the demos. Of course, now here in this webinar, we are a little bit limited. We will try to give you an impression through offline demos so that we can click, and a further impression also that you just get a feeling is how we demoed the codec in real time in South Korea. And of course, we finished then with a conclusion. Next slide, please. So for the background, and next slide, please. For the background, it's of course important to understand what actually we mean by immersive audio. So immersion in the audio domain means that this is, so to say, an experience really of being here or being there. So that the user who listens is really immersed or surrounded by a sound scene. And to make it a little bit more really clear what this means is if we also consider the case that what happens in real life is that if you hear something and you turn your head, obviously the sound scene would not move with you, but it would stay fixed in the room. So this is a very important property of immersive sound, so that there's something that, for example, stays with also a video scene that you would of course also not expect normally moving when you are moving your head. So this is one important characteristic. And if we look what this means in practice, is that we would most likely need more than mono sound, and then we do everything from stereo to 3D audio. Where it starts to be immersive depends a little bit based on the previous definition that the audio scene should really stay, so to say, at a certain position and not move with the head. Means, of course, that we would have to do something more than stereo, where if you have stereo headphones, of course, the scene moves with your head, right? So how is this applied in the IVAS codec? So normally we consider that we would capture either some natural listening environment, or we could also have the coding of a virtual auditory scene. So there will be some capture process. Then we have the actual encoder, sender, receiver, decoder chain. And then we have reproduction that we usually call rendering, and well, also receive side processing. And then we can feed it actually back into another natural environment or a virtual auditory scene. This is especially the case if we talk about things like mixed reality, augmented reality, where we have this kind of feedback into some existing scene. So this is just to give you the background, what we mean by immersive audio. And please next, Markus. So then, of course, when it comes to audio coding and rendering, this is nothing that is very new. So there are actually already many immersive audio coding standards deployed in streaming and broadcast and storage applications. We list here some of these codecs. And of course, there are certain immersive audio formats. So if we look into this a bit more on a technical level, and Markus will tell us more about this, there's something that is called channel-based audio, like everybody knows, for example, the 5.1 system. So this is 5 speakers plus a subwoofer. So this is, for example, channel-based audio. Then there's object-based audio and scene-based audio. And then we should also know that even for conversational services, there is already some predecessor, I would say, of immersive audio coding. that would be used also in certain services in the internet using the Opus codec. But the real novelty here is that we bring this immersive coding to conversational applications in mobile networks, so in 3GPP. So there is a special audio format that is designed especially for mobile phone capture, that is called Metadata Assisted Spatial Audio, MASA. And then we also provide here various new features. So there is some integrated JBM, jitter buffer management algorithm, integrated renderer and default binaural filter sets. So HRTFs is often known as a term. And then there's also something that is called split rendering that enables head track binaural audio on very low complexity or lightweight devices. So Markus, next slide, please. So just some history of the 3GPP IVAS work item. Essentially, what is the IVAS codec? It's actually an extension of the currently existing 3GPP enhanced voice services codec. So the EVS codec is actually a voice codec, a mono voice codec that is used in today's mobile or cellular voice services. So usually if you have some call where you turn on so-called voice over LTE, then you would, if you get good quality, then you get the EVS codec. And so the IVAS codec is an extension of this codec. So we have actually a chain of development steps that you see here. There's floating point code that was approved summer last year. Then we had some main specifications approved just this March. Fixed point code is in the development. We will have a characterization, so meaning that we have a technical report in the end telling how good the codec performs on various operation points. And all this package we target to be available in 3GPP release 18, which is something that 3GPP defines, which are all the features that would be provided, for example, with some kind of 5G or 5G advanced feature set. Important here for this work item is that it was really backed by major telecom players. So there, among them, we have operators, chipset, and technology vendors, German vendors, infrastructure vendors. So essentially the complete industry. And another very important thing is that the codec, and it's really, it has been a major undertaking. It was not developed by a single company, but really it was developed, as you saw already in the introduction slide, it was developed by many companies. And this was done under something that is called IVAS Codec Public Collaboration. So it was essentially open to anybody who wanted to contribute. And the process to contribute there is some kind of merit-based iterative approach, so that someone who likes to improve the codec with new technology would, of course, have to prove that the contribution really brings advantages. And this is then the iterative process how the codec was developed and was continuously improved. Next slide, please. So here, this is a perspective just how in 3GPP the voice services have evolved. It started all, well, actually about, now 25 years ago with the standardization of the AMR narrowband codec. So this is really a speech codec just transmitting the traditional narrowband voice band, so 8 kilohertz sampled with bandwidth of up to 3,400 or 3,500 hertz. The big novelty was there already that it was adaptive, so it was a multi-rate, multi-mode codec, so allowing to do rate adaptation. That was very important, giving operators flexibility to trade quality against voice service or network capacity. We then had similar concepts extending this then to AMR wideband with 7 kilohertz audio bandwidth and 16 kilohertz sampling rate. And then we got the standardization of the EVS codec, extending this concept even further. So there we got super wideband and full band support, making really the sound very natural and even for music very transparent. However, it remained just a mono codec, and the service that you experience is mono. But in any case, in each of these steps, there was always a quantum leap in terms of service quality for end users, but also in value for telecom operators. Next slide, please. I think the next is some illustration. So what it means to go from AMR, so that is narrowband voice, to AMR wideband, EVS, and then IVAS, which tells you how this sounds, how the immersive sound is. And hopefully you have stereo headphones for listening.
Vänta en stund så kommer doktorn.
Doktorn tittade i båda öronen.
Svenskarna trivs med solen.
Pojkarna spelade kula på gården.
Kalle diskade efter
motion gör
Båtarna har röda och
Stugan
gröna
är röd
segel.
med blåa knutar.
Vänta en stund så kommer doktorn.
Doktorn tittade i båda öronen.
Svenskarna trivs med solen.
Pojkarna spelade kula på gården.
Kalle diskade efter
motion gör
Båtarna har röda och
Stugan
gröna
är röd
segel.
med blåa knutar.
Vänta en stund så kommer doktorn.
Doktorn tittade i båda öronen.
Svenskarna trivs med solen.
Pojkarna spelade kula på gården.
Kalle diskade efter
motion gör
Båtarna har röda och
Stugan
gröna
är
segel.
röd med blåa knutar.
Vänta en stund så kommer doktorn.
Doktorn tittade i båda öronen.
Svenskarna trivs med solen.
Pojkarna spelade kula på gården.
Kalle diskade efter middagen.
Båtarna har röda och
Stugan är röd med blåa knutar.
Okay, so this at least gives some kind of impression what the differences may be. I have to say, maybe for the IVAS, but maybe this was just on my headphones. I did not really perceive a lot of speciality, but maybe this is just on my devices here. Let's turn to the next slide.
Vänta en stund så kommer
Sorry.
Yeah. Okay. So now let me turn to user expectations. Well, as already discussed previously, there are already end users are already used to immersive sounds. So they are in broadcast and streaming applications, of course. Such immersive sounds are essentially very well known to customers or consumers, and they know this from cinema experiences where they may have experienced some kind of Dolby Atmos scene or something like this. Then there's similar experiences are possible in home theater systems. There's of course music streaming, virtual reality applications, gaming applications. All these are essentially already giving audio experiences to and immersive audio experiences to consumers. However, what is really lacking in mobile communications is really this kind of immersive audio experience. And this is exactly the gap that we, as the set of companies, try to address in 3GPP to really provide this immersive audio experience in communication scenarios where we have really, since this is a mobile environment, we have to overcome various challenges. So they are highly mobile and uncontrolled capture environments. We have essentially to be able to render in various unconstrained environments. It can be headsets, it can be earbuds, it can be multi-speaker systems with any loudspeaker configuration, not just a very strict 5.1 or something like this. And then we will also have environments such as homes, cars, or conference rooms. So this is what the gap that we try to address. And next slide, please. And here, this is then, so to say, what the IVAS codec would enable in terms of service scenarios and use cases. So currently, well, and this is a little bit going beyond what the title of our webinar is. It's not only about meetings. We actually provide conversational voice even just for regular telephony, but it's then, of course, not any longer regular, but it will be stereo or even immersive. Of course, conferencing is a very important part of this. Important also to keep in mind is that there will always be the fallback to go to mono using the EVS codec because we have the interoperability. At least in the beginning, not every terminal, not every receiver will be that that the rendering will be done over stereo speakers or multi loudspeaker systems. So mono remains very important. So there we have the EVS codec. We have then the big new area with extended reality communication. So this is essentially telephony and conferencing bring into the XR space. And then we have the other field of live and non-live streaming of user-generated content and XR content. And here the 5 figures below are just explaining a little bit what kind of use cases we see, but these are just examples. So there would, for example, be telephony with experience sharing. So there's apparently maybe the father being out with his kids, taking a recording, immersive recording, sending it to the mother of the kids, and where she gets the impression as being there. Then we have a conference, ad-hoc conference call, where the capturing phone is just placed on the table, and the far end receiver will really hear the voices in a spatialized way. So hearing the talkers from different locations. There are, of course, immersive in-car audio experiences, considering that cars will more and more be equipped with high quality loudspeaker systems. We have XR conferencing experiences where essentially all participants would be remote participants, maybe having also some HMD, head-mounted display to see the other participants maybe as avatars. And then we have some extra streaming case in, well, it could be connected to some game or something like that. And I think that brings me to hand over to Markus.
Okay, thank you, Stefan. And then let's have a look at the technologies behind. So what we are here seeing on the slide is basically an codec architecture overview from the encoder or from the sender side. if we are starting at the middle of the image, and then what we are seeing here is basically the IVAS encoder, so which actually consists of several parts, but I come to that in a minute. And this encoder, well, basically it takes the audio that it gets, and possibly also the metadata. It produces some bit stream consisting of coded audio and coded metadata, which is then transmitted over the network. Of course, what it needs in order to operate is actually some input. So what is depicted here is like 3 possible input sources that correspond to the usage scenarios Stefan has just outlined. So that could either be content from the network, for example, from an MCU generating a spatial scene. It could be canned content from, I don't know, a distribution for a network, for example. And of course, it could be a microphone content or captured content from your mobile phone or from a microphone connected to your mobile phone. And of course, there is some sender processing or pre-processing required for that. So, for example, for the capturing the captured audio, it needs to be made suitable for the encoder. With the so I mean for mono, we know the usual stuff which needs to be done. So level gain control needs to be done, echo control needs to be done, possibly content needs to be reformatted, and then these audio channels or the format gets fed into the IVAS encoder, possibly together with metadata. And then what the encoder basically does is, yeah, I mean, what is depicted here is that so there are basically three core components depicted of the encoder. So the one is in the middle is the EBS interoperable encoder to generate an EBS bit stream. And then we have also here the IVAS core audio encoder to generate an IVAS bit stream. And below that's the comfort noise encoder to generate comfort noise, for example, if in communication scenarios where one of the participants doesn't speak. And that's something which is very unique to communication codec. So of course, like if the one participant doesn't speak, you can actually save a lot of bitrate and then also battery life of your device by turning that in the so-called DTX mode and just sending like small packets that just update the comfort noise. And that is sufficient to keep the connection alive. What we have here, in addition to the traditional encoder, that's of course also something which is called here analysis scene encoder and downmix. So that's something which is especially dedicated to the spatial scenes that it gets. Of course, we want to know what scene it is. We want to make the encoding easier by understanding correlations in the scene. And in case we decide that we only have a mono connection, then we possibly also can do a downmix and then feed that just into the EBS mono codec. The DTX front-end operation control, that's something I've mentioned already. So that's tightly connected to the DTX, so comfort noise feature of the codec, which is, as I said, used for inactive phases of the conversation. And then here is basically the equivalent picture of the decoder and rendering side. So maybe here to go from left to right. So what we are seeing then is, of course, we are receiving the bit streams then from the network. We have basically the equivalent blocks to the encoder here. So you have the IVAS core audio decoder, the EBS interoperable decoder, or a comfort noise decoder. And once this decoding is basically done, also with help of a jitter buffer management in order to compensate for potential network jitter, what we are doing then is basically it goes into a kind of a rendering stage in order to play out the decoded audio signal to the desired output formats. So that could be a rendering like, for example, a binaural rendering. That could be also scene decoder or upmix. So for example, in order to interpret ambisonic signals correctly, and of course, if packets are lost, we also IVAS also features a error concealment of lost frames, so that the lost packets are not annoying for the receiver. So the decoder can do the rendering. What IVAS also has as an additional feature is it has also an interface to an external renderer, which is also provided as part of the IVAS codec, but then also device manufacturers can also decide for implementing their own external renderer, for example, because that has certain features to differentiate to other manufacturers, or because it's specially optimized for certain devices. And then this rendered signal, of course, is played out, as that either on headphones or also alternatively on loudspeaker layouts. So a bit on technicalities for the coding part. As Stefan has already said, so IVAS, or the core coding of IVAS, is basically based on a modified EVS core coder. For you that you might not know how the EVS core coder is working, so that is basically a hybrid coding scheme. And if I say hybrid coding scheme, I mean it basically consists of two completely different codec types. So one is basically an information source approach with the ACALP. So ACALP is a traditional speech coding algorithm, and what this algorithm is doing is basically it's a physical model of the human speech production and by emulating this, you can actually code speech content in a very efficient manner and at comparably high qualities given the bit rates. So for example, one of the core bit rates for EVS is 13.2 kilobit super wideband, so meaning speech bandwidth up to 16 kilohertz, which is like the speech quality is really very, very good at this comparable low bit rate. The disadvantage with such an approach is, as I said, it's a source information source approach, is that it does not work very well for audio material which does not correspond to human speech production. So for example, music or a piano, for example, or complex music scenes. And for such scenarios, the second half of the hybrid codec is coming into play, and that is basically an information sync approach. And what this means is it basically emulates the human hearing and has its strengths at irrelevancy reduction next to redundancy reduction. So it basically shifts quantization noises into spectral areas that you perceive not very well with the human hearing. And by that, it so-called masks these artifacts. And maybe last sentence on these approaches. So the speech codecs, they typically work in the time domain. This is why it's also called switch time domain approach, and the information sync models. These are typically transform codecs that work in the frequency domain, and thus we basically have at the low bit rates a switched time domain frequency domain coding scheme. Apologies. And then towards the higher bit rates, basically one does not need the time domain approach anymore, and to scale to transparency, then for that really only a frequency domain coding scheme is used. The EVS core coder, or the basis of this EVS core coder, it had to be modified, especially to allow for variable bitrate coding. since we now also have to take care of certain metadata or spatial site information. And there were also a lot of optimizations done with respect to complexity, and then also to make things like joint coding of channels and also the packet loss concealment better. If you are looking inside the IVAS core coder, you basically notice that there are 3 different elements to do various coding. So first of all, we have a single channel element, and as the name says, so by means of this, you can basically feed in one channel and it codes this. Then we have a channel pair element where you can basically feed in a stereo signal, and it takes care of this by special stereo coding mechanisms to either provide a parametric representation of this or to at least exploit redundancies between the 2 channels. And then we also have extended that towards more than 2 channels, and then this is now a multi-channel coding tool where especially redundancies of more than 2 channels are exploited. And so the next slide basically illustrates why we need this. And so that's a very high-level overview about on spatial coding paradigms. But so what we are basically getting is, like, on the encoder input, we are getting a number of input channels. So that could be, for example, for mono, of course, you get 1 input channel. For stereo, you get 2 input channels. For, let's say, multi-channel 5.1, you are getting 6 input channels. And for ambisonics, for example, you are getting first order ambisonics, you are also getting 4 input channels. And the challenge is now to represent these channels in the best possible manner, given the available channel capacity, which directly translates into bitrate. And so one of the findings is, of course, that if you have a smaller bitrate budget, let's say 13.2 kilobit, you have to implement a different approach than when you have, for example, a very big bitrate budget. So for example, if you have 512 kilobit, I mean, you have like almost 50 times the bitrate compared to the 13.2 kilobit. So what the encoder basically does for all spatial formats is basically it decides here in this first block, which is called analysis scene encoder down mix. It basically decides how many transport channels one could allow for the given bitrate budget. Then, for example, at 13.2 for, I think, basically all the formats, the decision is, well, we only can allow for 1 transport channel in order to code that in a sufficiently good manner. And but what do we have to do now with the information that we have, for example, derived from the first order ambisonic signal or from the 5.1 signal? So we need to represent that somehow. And the solution to that is that we can represent that by means of a parametric approach. Namely, we extract spatial parameters, which are dependent on the actual formats that we are using. And we store that we store that in site information. Also sometimes with the help of additional metadata, and stores it in the bit stream. And like this, spatial site information can be compressed very well. So we are talking about 1, 2, 3 kilobit of bit rates that we need. And the rest, so for example, in the 13.2 kilobits, the remaining 10 kilobits or 11 kilobits, we actually then can spend for coding this 1 transport channel here by the SCE encoder in a sufficiently well manner. And then basically these 2 things go into the bit stream. And just to come back to the other extreme. So let's say, for example, we have a first order ambisonic signal and we have 512 kilobit. Of course, like that is more than 100 kilobit per channel, basically, because we are inputting only 4 channels. So there is basically no need to extract to extract spatial parameters in order to reduce the number of transport channels. Of course, that's always helpful in order to redefine the scene and to make the compression very efficient. But actually, for this scenario, we can just allow for 4 transport channels and code these then, for example, with the MCT tool, which takes care of reducing the redundancy from these channels. And yeah, I mean, there are also scenarios, of course, in between. So there might be bit rates where we decide for 2 transport channels, and then these would go into the CPE encoder. And it's basically the expertise of the codec to make the best decision where to spend the bits most wisest in order to get the maximum quality. I think I've explained basically all of that. So we went through the parametric approach where you extract parameters to describe the spatial features. And for cases where the bitrate is high enough, we just go with the discrete approach where we then can like represent these channels in a discrete manner, just exploit the redundancy among the channels, but can more or less decode it with traditional coding scheme. Which something I did not mention so far. So some formats also include explicit metadata, which needs to be coded explicitly. So this is basically this branch here over there. And the 2 formats that we are basically talking about is objects. So of course, if you have an object representing a speaker in a scene, you also want to convey certain coordinates where exactly this speaker is in the scene. And the other format I have not mentioned so far was the metadata assisted spatial audio format, the MASA format, where the spatial metadata representing the spatial scene is already extracted during the capturing. So what basically arrives here is then like 2 input channels, which basically transport already to the correspond to the transport channels, and then you have additional metadata representing the spatial scene. So that was a brief walkthrough through the coding. Of course, we could add a couple of hours explaining the different concepts, but we don't have enough time for that today. Another interesting aspect is the rendering. As said before, so IVAS comes with a number of rendering schemes already attached to it, which are either part of the renderer or the decoder or the external renderer. So I mean, probably most relevant for most of you right now is the binaural rendering, so that you have a spatial scene and you basically convolute it either directly with an head-related impulse response, and generate by that a binaural stereo signal to listen to via headphones. So we have, of course, some regular binaural rendering with some default HRIRs equipped as part of the IVAS decoder / renderer. And in addition to that, there are also impulse responses for rendering rooms. And there's also a parametric reverb where then the user or the application can actually modify parameters and simulate various rooms and room characteristics. We have a binaural split rendering feature I'll explain in a couple of minutes. And of course, we have also loudspeaker rendering to various layouts. And the layouts are basically the most used layouts these days. So of course it's mono and stereo, which is included, but then there's also support for schemes like 5.1, 7.1, 5.1 plus 2, 5.1 plus 4, and 7.1 plus 4. The advantage, so I said, so the renderer is basically integrated in the IVAS decoder, and that is a very efficient implementation because you can, for example, share domains between the decoder and the renderer. So as said above, so We are also working in the frequency domain, and of course certain steps. So for example, a convolution you can do with a relatively efficient multiplication directly in the frequency domain. And thus this is very not only computational, very efficient, but you also can actually save some algorithmic delay by doing so. There are various implementations of the rendering schemes implemented. They are always optimized to the transport, decoding, and output format in order to actually really get the best performance. For on rendering side, we have 5, 10, and 20 millisecond resolution. So 20 millisecond because like that's actually the IVAS frame size of the IVAS codec, but we can, for rendering, we can reduce the resolution actually to 5 or 10 millisecond in order then to make, to reduce the motion to sound latency for things like head rotation significantly. And as also said before, so there's also an interface in order to connect an external renderer. So IVAS also comes with an external renderer, but implementers can also connect their own external renderer. This external renderer can also be used as a preprocessor for certain applications. So of course, like if you can on receiver side render, let's say ambisonics 2 stereo, you could also imagine of doing so on the sender side. But so there might be applications where this is beneficial, but in general, since you have also these parametric coding schemes, it's not really needed. Yeah, so this picture here in the middle, it basically illustrates it. So we are getting the transport channels, we're doing decoding and then rendering. As said, so we have a post control by also implementing head rotation, and there's also metadata control in order to, for example, control the parametric reverb. A special feature is also the split rendering concepts that comes with IVAS, and maybe I should spend 1 or 2 minutes to outline the use case of that. So split rendering is especially helpful if you have a very lightweight device you wanna, for example, use for the sound reproduction and possibly some other scenarios. So for example, that could be such VR or XR glasses. And of course, from a user perspective, these glasses can't be light enough. And of course, they should ideally not come with a cable in order to optimize them for user experience. And of course, they also should not heat up. But I mean, these are actually like if you have to do a lot of heavy processing, not only, for example, for the audio, but also for the video processing, actually that might simply lead, if you want to do that on the glasses directly, that might lead to effects that you need a somewhat larger battery, which adds weight. You need to add a somewhat larger processor, which heats up, and that is really not adding to the to a very comfortable experience. And what we have already right now in the market is to basically split up the processing into 2 parts. So to do the heavier processing in, for example, the smartphone, and then transmit only a reduced representation of the video and audio scene to the glasses. So for video, what is done nowadays is that like a slightly bigger fraction of the viewport is decoded on the smartphone, and that is transmitted only, so that you don't have to decode the complete 360-degree scenes, and then just like the actual viewport is adapted. And we have now adopted a similar concept also for the audio, where then the IVAS decoder and the renderer is actually performing so-called pre-rendering of the audio scene. So it's basically carrying out different binaural renderings of the scene. These are basically then fed into a split renderer encoder, which extracts metadata out of it and a stereo representation of these binaural renderings. And both is done with relatively lightweighted processing, which is of course not as efficient as the IVAS codec, but for the relatively short distance between the smartphone on the glasses, so that's just fine. And the optimization here is really to be relatively low in additional algorithmic delay, ideally to add no additional algorithmic delay, and to be very lightweight in the encoding and especially on the decoding process. And as said, so we have here a block which extracts some guiding metadata for how to adjust then the split rendering, and we have two dedicated codecs which are very lightweight, which operate in different domains. Again, it depends a bit on which domain you are already in the decoder. And then what only happens then on the lightweight device side is that you have really a low complexity decoding. You have a look at the metadata, and then you just slightly adopt the decoded binaural rendering scene in order to also compensate for the small delays that you have between the presentation engine and the end device. And that is working very well. Good. I think I've mentioned all that. I think I need to speed up a bit. One of the points that also needs to be taken into account is, of course, what's also important for IVAS is the audio capturing, as Stefan has already said. So if we want to capture a spatial scene, we need definitely more than one microphone connection. So for stereo, we need at least two microphone signals, which correspond then to at least two capsules, 3 or 4 for 360 degrees, or for real 3D spatial capturing. And so IVAS does not come with an audio capture implementation itself. However, there's standardization ongoing, or there is standardization work also ongoing in 3GPP in order to provide guidance to the implementers to do so. That comes with, of course, new challenges also. So we need to acquire zero microphone signals, compensation of microphone self-noise and frequency response, acoustic echo cancellation, potential wind noise estimation reduction, spatial audio format generation, and then also leveling, so HEC and limiting. But I said, so there's some guidance work in 3GPP ongoing. And especially for MASA, there are also examples that are already right now captured in a technical report, and also for SBA on how to do that. Okay, then coming to codec characteristics. So I think I mentioned already some of that before. So IVAS supports a number of audio input formats. So of course, channel-based audio, stereo, and multi-channel. I don't think I need to add more than that. To that, we have support for object-based audio, basically for, you can code 4 independent objects at the same time at max. They are called in IVAS independent streams with metadata, and of course they come with some object position. We have support for scene-based audio or ambisonics up to order 3. Then metadata assisted spatial audio, where you have some spatial metadata and then 1 or 2 audio channels, which basically correspond to transport channels. We have combined formats, so you can combine objects and ambisonics or objects and MASA. And we also have mono support by support of the integrated EVS compatible mode. Okay. Then in terms of bitrate, so of course we have full EVS mono compatibility, so that goes from 5.9 to 128 kilobit. And then all the spatial and stereo and multi-channel formats, they basically start at 13.2 kilobit, and it's a bit dependent on the format, the maximum bit rates that we have for that. So stereo only goes to 256 kilobit because I think more is really not needed. It's really transparent there. And all the other formats go up to 512 kilobit. With respect to delay, it also differs from the format. So mono and stereo, we have the EVS codec delay of 32 milliseconds. And for the other formats, it's actually dependent on the rendering, and that is between 32 and 38 milliseconds delay. We support all nowadays important bit rates, sampling rates of 16, 32, 48 kilohertz, which are established in the communication world. So not 44.1, but that's really not the standard from my knowledge. We support for spatial coding wideband, super wideband, and full band audio bandwidth, and narrowband only for mono. So for spatial audio, narrowband really doesn't make any sense if you're looking at the complete user experience. As said before, loudspeaker and head track by no rendering is supported, and yeah, the combined formats I've mentioned already. And so there are currently, that's currently still in discussion, complexity and memory levels. So there was a requirement for support of 3 such levels. So level 1 is smaller or equal 3 times the EVS complexity, level 2 6 times, and level 3 10 times EVS complexity. These levels are not fully defined, so this discussion is ongoing right now, and we are also still waiting for the fixed point code to be available, but I think it will be defined in the near future. Good. Then we did for the codec selection, we did a lot of testing actually. So 319 requirements were tested in a lot of P supplement 800. So it's basically P800 tests or Masha tests. The requirements were really met in almost 100% of all cases. We had, if we had systematic failures, we always had 2 labs running these tests in parallel, so they were never replicated in the other lab as well. Yeah, so with that, the conclusion from our side is really IVAS is unique 3GPP codec enabling efficient provisioning of immersive user experience in communication services over 4G and 5G networks. We have a lot of listening test results. I will not discuss these point by point, but just for illustration, so maybe I spent a bit more time here on the first graph. So that was a graph for stereo, and the way the selection tests were set out was that we were basically comparing the IVAS performance, which is here in the red curve, against the performance of n times EVS. That was in the blue curve at the same bitrate, and what you can see here is that there is quite a significant gap, which is really big at the low bit rates and gets slightly smaller towards the high bit rates. I think that's the general pattern that we can see. And so the reasons for this gap is really, I think, twofold. So of course, IVAS is specialized for exploiting redundancies between these input channels. But then also, I think the second aspect is really like if you're coding these 2 channels separately, for example, for stereo, we are mostly talking about correlated content. And if you are just coding this correlated content independent of each other, you might actually get effects by the so-called demasking of quantization error. So if you are not taking the 2 channels into account for joint coding, you might basically get uncorrelated noise in the decoded channel, and then that modifies the spatial image. So as that, so here's stereo mixed music performance, for example. We have here results for clean speech first order, and of course what we are also seeing here, so here we start already at 16.4. I mean, that's something which is not even supported by N times EVS. So there it starts, I think, at 28 point something, if I have that correctly in memory. Then we have also clean speech performance data for MASA. We have 5.1 results. So these are Masha results actually from 2 different test sites, where we can also see a clear improvement. And yeah, that's it basically from my side. If you're interested in more test results, we have a report out there. Please don't be shy and approach me. I can show you that afterwards. Then Stefan, your turn. Yeah.
Yeah, thank you, Markus. So, yeah, what I will do now is just to give you a very quick impression of what the 3GPP IVAS codec means in terms of standard specifications. So, Markus, please, next slide. So, typically, of course, we describe the codec itself in something that we call core specifications. There is what you would expect is, of course, that you have some kind of cookbook specification that we also call algorithmic specification. So this is the specification here in the middle, 26.253. This is a specification that is about 700 pages or something like this. So there you can, and it really contains a lot of, well, of course, detailed algorithms, mathematic formulas, and so all the methods that are being implemented in the actual standard. So this is very important to give implementers some kind of reference to see how things are actually working when they are implementing the codec. But of course, what they also need is, and in 3GPP, this is the case, they want to have a source code that implements the codec. And so what is currently available is the 26258, the floating point specification. Here we have both encoder and decoder source code available. And this package contains everything that you need, including rendering, including jitter buffer management, frame loss concealment. All these things are included there, which is not an obvious thing. There are other standardization bodies or other standards where, for example, only the decoder is specified. So this is really of big help for implementers. Then along with such kind of source code specification, there are usually also test sequences allowing to verify that an implementer has really implemented the codec on the target device in the proper way. Normally, these test sequences work well with fixed point code, not so well with floating point code, because for floating point code, this is very difficult to have it well, on a different platform implemented with really bit exactly the same result. So this is why we are still waiting very much for the fixed point code that is expected to provide exactly the same performance, exactly the same functionality, but can then be implemented on, for example, smartphones in a more efficient and mainly power efficient way than the floating point code. And then we have also things, description of the RTP payload format and STP parameter definitions. They are part of the algorithmic description. And then we have separate specifications on rendering, on error concealment of lost packets, and jitter buffer management. And I mentioned already in the beginning, there will then also be a full technical report that summarizes all the characteristics of the codec. It will contain not only the quality figures that Markus showed just previously, but it will also essentially bring all the results from the various listening tests done in the selection of the codec, but it will also provide results from new tests where we evaluate, for example, the performance of the fixed point code. It will provide data related to complexity of the codec, delay of the codec, usually also on things like frequency response and such kind of properties. And this is essentially the core specifications of IVAS. But if we look now at the next slide, having this would essentially just mean that that we have a codec, but it would not tell how to use the codec in 3GPP systems or 4 or 5G systems. To have really the system integration, we have the so-called IVAS system specifications. So these are specifications that have already existed, but we have to add IVAS codec to these specifications to tell how the codec would be used. So there's one very important specification, 26104, which is on multimeter telephony. So there we are in the process of adding IVAS support. Same thing for 5G media streaming, for messaging. And then, what is also very important is to keep in mind that we are also dealing with the codec to be, or the codec data to be negotiated by 5G core network. So there are certain network nodes that have to know what the IVAS codec is, how to interwork with, for example, other networks, when to downgrade, for example, from IVAS to the EVS codec, and so on. So this is covered by so-called core network specifications. So there are actually also quite a long list of specifications, and also here we have to add the IVAS support. So most of this work is still underway. Some of this is already done, but also here we are targeting to finalize this by mid of this year. And then we talk also about adjacent specifications. One set of specifications related to the terminal audio characteristics. So there are certain requirements that the terminal, so the audio interface of the both on the rendering side and the capturing side has to meet, and there are also certain requirements that will be test methods that will be defined to show that the requirements are met. And then Markus mentioned this already. There's a study ongoing on it's called here diverse audio capturing system. It means really it shows ways how to do immersive audio capture on devices like smartphones. And next, this is now essentially we are coming to the end of this webinar, or at least this presentation. Here are a couple of use cases encoded with AMR wideband, EVS, and IVAS. So you see the bit rates for AMR wideband and EVS. We are spending roughly 24 kilobits per second. For IVAS, we allowed ourselves a little bit more. However, that said, it does not mean that IVAS does not work even at 24 kilobits per second, roughly. So in fact, 24.4 you would also hear a good spatial audio quality. Markus, shall we give it a try to that you click, so to say, through the different use cases by codec so that we get an impression of what happens?
Yeah, maybe we start with the first row. And please, you need to, Stefan, maybe you can listen whether you hear the special image sent for IBUS.
I guess, I don't know, maybe it was just a setting on my headphones.
There's, of course, also a setting to share stereo. So we tried that before, but maybe I've done something wrong here. Let's give it a try.
Let me just add here, Markus and Stefan, that it worked just fine here with me. So hopefully it's the same with the audience.
Great, thank you. Yep.
This is a grand season for hikes on the road.
We tried to replace the coin but failed.
The jacket hung on the back of the
small
wide
pup
chair.
gnawed a hole in the sock.
Adding fast leads to wrong sums.
The office paint was a dull, sad tan.
A speedy man can beat this.
Use a
trademark.
pencil to write the first draft. This is a grand season for hikes on the road.
We tried to replace the coin but failed.
The jacket hung on the back of the
small
wide
pup
chair.
gnawed a hole in the sock.
Adding fast leads to wrong sums.
The office paint was a dull, sad tan.
A speedy man can beat this.
Use a
trademark.
pencil to write the first draft.
Okay, so that was AMA Whiteband and followed by EBS, and now we have IBUS.
This is a grand season for hikes on the road.
We tried to replace the coin but failed.
The jacket hung on the back of the
small
wide
pup
chair.
gnawed a hole in the sock.
Adding fast leads to wrong sums.
The office paint was a dull, sad tan.
A speedy man can beat this.
Use a
trademark.
pencil to write the first draft.
Okay, Stefan, should we walk to all of them, or do you have a preference for?
I don't know how it is with our time budget. Maybe we should, since essentially this demo material is essentially also available on the link that we provide below. Maybe we should move on so that we have also still some time to in the Q&A session. Or what do you think?
That sounds good, Stefan, to maybe wrap your presentation up and just have a few questions. Do you have anything to add here before we go to the Q&A section?
I think, of course, here, but this would also be something for you to look at just as some kind of illustration. At the ICAST conference, we also showcased really real-time demos operating on tablets or smartphones. So there was one demo where we showed essentially also the different service scenarios, use cases, so multi-party telephony, conferencing, immersive messaging, and streaming of UGC, and we did it in a way that we had real-time decoding on an iPhone, so that it was really possible to switch between bit rates and between codecs, even making use of the feature that EVS and AMA Whiteband are included in the IVAS codec. And also, the very important thing was that here there was also head tracking that was supported, that is giving a very strong effect. And the next demo was a demo where we have essentially another very important feature of the IBUS codec that is related to object audio, or we call it ISM, so independent stream with metadata. So where it is possible to transmit, for example, several objects, meaning, for example, several speakers at different locations, sending them to the receiving end and allowing the receiver at the at the receiving end to modify the positions of these objects or talkers. So this allows then really for very interactive experiences So, for example, in a conference, you could then really imagine that you can place your speakers where you want to have them, or the talkers. You can attenuate some talker that you don't like, that is disturbing, things like this. So this was done also in a real-time way. And then we had a third demo that is also using rendering on an iPhone. And here, especially, we had a comparison between the two audio formats, Master and SPA, also with head tracking. Here again, illustrating the value of head tracking. And I think that is just from some kind of illustration what we've done. So as a conclusion, what we think is that the IVAS codec is really the universal solution enabling for the first time sharing of immersive audio experiences, both for conversational and non-conversational services in 3GPP, so 4G and 5G networks. And a very important feature is the interoperability with the existing EVS and AMR wideband speech codecs. So that really the IVAS codec is essentially just evolution of these earlier coding technologies. And what we are convinced of is that the IVAS codec will transform the user experiences in cellular services like telephony, conferencing, messaging, and UGC sharing to a completely new immersive dimension. So this will really make a huge difference. And that's it from, I think, our end.
Okay, thank you very much, Stefan and Markus. Let me just say that is it correctly understood that the audience will have accessibility to your demos afterwards?
So partially.
Yeah.
So,
anyways, we will send a follow-up email, and we will put the material that we can for people to dive into. But anyway, during this webinar, I asked a couple of questions to the audience, and I would like to hear your perspective, and then I'll reveal the answer among the audience. As regards to audio quality development, what comes first? Knowledge and technology, or user habits and demands? And you, Markus, do you want to go first?
Yeah, I'm not sure you can clearly answer this question. I think both go hand in hand for me, actually, because of course there are demands for better audio, but then sometimes also people don't actually know that they want to have that, because like if you like 30 years ago, if you would have asked somebody, well, is there a need for more audio bandwidth at telephony than 3.5 kilohertz? I mean, probably people would have said, well, I understand if whenever I call my own, so that's just enough for me. But I think like with nowadays quality, I think you really don't want to go back anymore. So I think it's both probably going hand in hand.
Right. I know there's not a simple question, a simple answer to this question, but I can tell you that the audience, 56% said user habits and demands, 44% said knowledge and technology. So yeah, they go hand in hand. I can definitely see a sense in that. Then I also asked them, what has the biggest impact on audio quality and speech intelligibility? Is it coding, the space the source is captivated in, audio hardware, or audio software? And Stefan, do you dare to give an answer to this?
Well, I have to say, of course, it depends very much on the codec, but I would claim that we have presented the codec that solves very much the so to say the coding issue. So the codec itself is not any longer really the bottleneck. So we provide really very real audio experiences, so that are really indistinguishable from reality. Of course, there are certain bitrate requirements, but even at relatively low bit rates, we provide really very great experiences. So this is, in my view, not any longer the bottleneck. But of course, what plays into what plays an important role is really where in what kind of sound environment are we doing the capturing. Of course, it's also how are we doing the capturing. So this would be most likely the one that I would set first.
All right. Well, I can say the answers were split among the audience as well. 33% saying coding and audio software, 17% saying the space and the audio hardware. So yeah. I have a couple of questions from the audience. One here is asking, shall one buy new mics to use IVAS codec, or can old mics be used?
Okay, I don't know who is going to answer. Maybe I can take
sure,
the first.
Sure, yeah.
Well, it depends a little bit on what you want to do. If you really want to do immersive audio, then you and you really want to try it, then of course one possibility would be that you buy some ambisonics microphone. So it would, for example, for first order ambisonics, it would typically have 4 capsules. For second order ambisonics, it would have 8. You get such kind of microphones in the order of well, maybe €1,000 or something like this or below, depending on the quality of the device. Of course, you can, if you think that stereo is sufficient, then you can use obviously also existing stereo microphones. So there I would not really see a limitation. And of course, depending on what kind of access you have to what kind of audio capture environment, for example, if you have equipment to do multi-channel audio recordings, they can of course be used.
Okay, thank you, Stefan. I have another question here. Is it possible to obtain documents and code not being a 3GPP member organization employee? Maybe Markus, you want to answer?
So the specifications, which also includes the source code, so they are publicly available to basically everybody for download. Of course, of course there are 3GPP what to say conditions bound to that if it goes really to implementation, but for just yeah, I mean, everybody can download it. Just go to the 3GPP website and either you search for 3GPP IVAS or you go to the 3GPP 26 series of specifications, and then you will find it there.
Yeah, or you simply Google for the specifications that I listed on one of the last slides.
Perfect. That was easy. Okay, gentlemen, I think time is up for today. I want to give a big thanks to both of you for sharing all of this experience and expertise with us, and I'm very much looking forward to how this will be integrated in everybody's lives going forward, and see it as part of our everyday life. And now I would just stop sharing your screen and take over from here, Markus. And just say thank you very much to you, Markus Multrus, and Stefan Bruhn for joining us today here. And there we go. Thank you very much for joining the Danish Sound Cluster. We are a member organization in the sound industry, and we would love to hear from you. And you can go follow us on YouTube, where this webinar will be recorded and it will be shared probably tomorrow. So you can go and watch the full length if you missed any of the action. And go follow us on LinkedIn for many more webinars and events. We have one coming up next Tuesday, actually. We are staying we have a German week here at Danish Sound Cluster, because we've invited Oliver Nieburg and Björn Schuller for a very exciting talk about the impact of the human voice, and where we explore the hidden layers of meaning. And I would like to also encourage you out there, if you want to collaborate with us, please reach out. If you work with health and hearing, acoustics and environments, and sound experience, you have the opportunity to join an innovation project with product innovation, process innovation, marketing innovation, or organization innovation. If this could sound interesting to you, please go to our websites, where we have a list of all the completed collaborations and also the collaborations we are working on at the moment. And please reach out to my colleague Tine Midgaard, who will help you if you have any questions or queries. That's all for now. I hope to see you some other time. And thank you to both of you once again. And thank you for everybody showing up. I'll see you next time. Bye-bye.
Thank you.
Thank you. Bye-bye.
Bye.